And we're really pleased to be hosting this. And actually, we're first in all, as we are in New York, we're always first. The third thing is congratulations to Ragnarok Industries. Kyle, Luigi are here. Raise your hand. Stand up. Raise your hand. So these guys, Ragnarok, won. Well, they were a first round prize winner in NASA's Cube Quest Challenge. Big round of applause. So yeah, they were 1 in 5 teams that won $20K, and next phase is we call it Ground Tournament 2 in February. Right. So any questions about Cube Quest or any of that? Talk to these guys. I'd now, let's see, like to go to
the first one.
The first one, yes, that's already telephone. Cool with you. We unfortunately this is moving. That's not what you want to say. That's St. John.
There it is.
Okay. I would like to introduce Big Vilas. Babe, I'm gonna introduce you. I have like 2 pages of your accomplishments. Faith is gonna talk about some of those. I know she's modest, so I'm gonna tell you some of the things that she's done, although she'll cover it too. But she has over 30 years of experience in planetary science and astronomy. One of the great aspects of this is she's maintained a hand in observational astronomy. So that means she's conducted research all across the globe, from Guam to Antarctica. She may talk about that. She has a very long list of accomplishments that she will tell you, but including working for Planetary Science Institute, director of the MMT in Tucson, and with NASA for about 20 years, and in NASA headquarters. But what I think is really cool is the things that she's not going to tell you, and that is, so before she got her PhD, she worked for Lockheed. You probably know. She analyzed orbital X-ray fluorescent data of the moon from Apollos 15 and 16. And she also worked for she'll talk about this, Suborbital Inter-American Observatory in Chile. And she is one of the discoverers of the rings of Neptune. That's true. Can't dispute that. And she designed the coronagraph used to produce the first ever image of a circumstellar disk around another star.
A long time ago.
Long time ago. Long time ago. Mercury Messenger mission. And then in 1989, she was honored by the International Astronomical Union with designation of a minor planet, 3507 Vilas. She's also a pilot. Her grandfather, Jack Vilas, was the first person to fly across Lake Michigan, and 2 years ago?
1913, so 2013.
2013, she recreated that flight. She's also an animal lover, interior designer. Welcome, Faith. Let's give her a big New York
I'm sorry. If you want me to sit down, I will.
Oh, no, it's fine.
I know whether I should be seated or stand, so I'll stand until I'm seated. And please, and I'm told by Kathy that you'd like to interject questions. I'd be happy to take questions anytime. I'm probably not going to talk as much about my background as Kathy would, think maybe. But I have been in planetary sciences and astronomy for many, many years, too long to want to have to admit to all the time. But I've been an observational astronomer. I went to college to study observational astronomy, and I'll just quickly review my background without all the embellishments that Kathy so kindly gave. So the first one is just my background educationally. I got a bachelor's degree from Wellesley in astronomy and started doing research with a prof at MIT and segued into getting a master's degree at MIT in Earth and Planetary Sciences. As part of my research, he said, I will send you to Chile to observe Mercury, the planet Mercury? And I said, I don't want to go to Mars. And he said, I'll send you to Chile. And I said, I will go. And I went, and I fell in love with Chile. And I talked them into hiring me as a research assistant, computer programmer, a bunch of things like that. And I jumped off the grad school thing and went down to Chile and worked there for a couple of years, took off with a backpacked around the southern part of South America and then some. And then returned to the US, worked for Lockheed for a year analyzing the X-ray fluorescence data while I was applying to go back to school to get my PhD, because I realized that in Chile, they were happy to have people who were of any background working there. But once I got back to Lockheed, I was going nowhere without my PhD. And my thought was, if you're not brilliant, which is me, then you've got to be marketable. So I also worked on instrumentation and image processing, which was all new types of things at the time. So I went back to the UK, got a PhD in planetary sciences, and I designed a minor in instrumentation and I did a lot of systems engineering. And so I have sort of a mixed bag background and very much enjoy instrumentation, and thought I would do more of it. The instrument that I designed, the chronograph, my PhD advisor and a colleague of his did the image of the Circus Stellar disk around Beta Pictoris in 1984. So I designed the instrument, he did the observations, and I have to give him credit for that. But I got probably hired by NASA because of that. So I'm happy I got my sense work out of it. And go ahead to the next one. Then education sort of continued. I was in Washington for a year working for NASA headquarters, and I started to work on the Certificate of Legislative Affairs, figuring I should learn what the heck people are doing to get funding with NASA, and I never have really yet, but I did finish this, and it was pretty interesting at the time. And then, go ahead. I also, in a total side thing, I guess I have formal education from San Jacinto College in becoming a licensed paramedic in the state of Texas, and that takes care of the side of me that wanted to go to medical school and never did or will. So, but I've enjoyed that a lot as well. And so that's probably the end of my actual formal education. Thank God. Periodically I kept saying, oh, I'm gonna go off and do this. I never did it. I stayed where I was. So go ahead. Work-wise, I mentioned I worked for Sarah Tololo back from 75 to 77. It had its interesting moments, and I have a very strong love and a very strong love-hate relationship with Chile. It's my second home, but it's a very different situation going from being a college student in Boston to what was then very much provincial Chile in the mid-70s, and being the first U.S. female to work on that. That being said, right now Chile is in my heart because of the earthquake and the tsunami that wiped out a whole chunk of majoring town. The La Serena, where you live, merges with Coquimbo, which is a port, and it's, well, for practical purposes, almost the same. And a good chunk of the tsunami that hit wiped out a lot of the fishing industry, a lot of some older buildings, and then in the last day or two. Mm-hmm. And just it's hard. Anyway, worked for Lockheed. Go ahead and switch on. Then when I was done with my PhD, I went to NASA, JSC, in pursuit of being an astronaut, which I didn't become. And I'd say 50% of the people on site want to be astronauts, and the other 50% wouldn't go into a tin can if you paid them. But I didn't become one, and I tried. I got trunked my way through it, but medically it just wasn't going to happen. So I worked there until 2005 with 1 year at NASA headquarters from August 2001 to August 2002. So it was a pretty interesting time to be at NASA headquarters. I was running the selection for the Discovery program of the missions that have now flown Kepler and Dawn. And so I was the Discovery program scientist at the time. And that was an interesting situation also because telling 2 cents worth of other stories. And I had a site visit to happen at Orbital, which is in Dulles, scheduled for September 12th of 2001. So all the Europeans and other people on the team were coming in to be assessed. My team was coming in to conduct the assessment with me, and we all got stuck. Most of us all got stuck in, or they got stuck in DC on the 11th, of course, and we're stuck there for a while. And that was an interesting times. My attitude toward it was the U.S. does the space program really well. It's one of the things we do really well. And I would be damned if anybody was going to stop the selection or slow it down much. So I really forced through the selection process. Probably only slowed down by about a month as a result of that. With the very honorable participation of the team that hadn't gone through assessment, it was scheduled for 12 and the other two teams had. I figured out a way to make them be honorable, and they were as well. So it was. Anyway, in 2005, I jumped the ship with NASA and went off to become the director of the MMT Observatory, going back to doing more of my ground-based observing. Was at the MMT as director for 5 years. And then I left that because I'd started working on a project that I will talk about tonight. I left that to join, it was all there. Cool picture of me, hashtag girls with toys. If you heard of that campaign, I think I put one of those up there. That's me going up to take a look at the primary mirror, which was 6.5 meters. There's only one mirror there now. Primary mirror is 6.5 meters, is roughly 23 feet in diameter. And I was going up to check it. You'll notice I have a safety harness and stuff on it because I could just easily trip and happily fall this way. I wasn't going to fall. And since I was demanding that everybody kept strict safety things, I had to go with that too. So there I am going up to take a look at the mirror. The problem with the MMT, and it's not a problem, it's just a unique aspect of it, is that because it was a retrofit to a building, I was talking about this a little earlier, we have to re-illuminize the mirror in situ or in place. We can't pull the mirror out of the telescope and re-illuminize it elsewhere. We do it there. So I was looking at it in prep for what we were setting up to re-illuminize, which is a major event. We have to bring in a thing and put a bell jar in over the whole thing, just take apart a whole bunch of stuff. And then it becomes pretty interesting. But it's lasted. I think they're probably going to re-illuminize again next summer. But we've developed ways of preserving the coating over long periods of time, cleaning it, and then re-illuminize it. Anyway, so I left the MIT to join the Planetary Science Institute, where I am now. I'm a senior scientist, and I'm also the project scientist for a project called the Atsa Suborbital Observatory. This is actually how I originally met Kathy, and through suborbital space. And the critical thing about Atsa is, here I am doing a test fit. We did the fit of one of our first configurations of this with the other person who is my partner in this project, Luke Solid. He's a professor at the Citadel, and had before that been at Northrop Grumman. So we're doing fit testing of our first configuration, which we then scrapped and saved about 2 pieces of and have completely configured as a result of that. However, it's about the same size, and I'll show you a configuration of that later. I'm still with PSI. I'm a senior scientist. PSI is a fully soft money organization. So I've gone from being within the structure of NASA, which occasionally drives me crazy, to PSI, where you occasionally sit there and sweat bullets over whether you're going to survive financially. Oh well, it's been interesting. And so anyway, that's me with Luke doing fit testing. I think that's probably 2012, I think. And is that right? And it's in the X-Core Aerospace, obviously links the engineering. We are ready to go, and they've been so far said yes, and they keep putting us off a couple of months because they don't want to be interrupted in their construction of the least one. But we really want to go into the one that's going to fly, because that's what we want to fly it. So, at least this first round, So we're sort of saying, okay, And some people would like us to come because they think it would cheer up the people who are there to see some real space hardware coming up. That's right. And we do great things, And other people say, wait a minute, we just really need the time to work. So we're patient. We're ready to go with our final configuration, although I don't have pictures of it here. But our final setup, all the hardware is pretty well done. We have a couple of tests to run, but I'll get to that. But we're, for the first round of the Atsa. Atsa is the Navajo word for eagle. It doesn't stand for, it's not an acronym of any sort at all. We just picked it out because we liked it. You can see that in we're a real project because we have although that makes us real, hey, you know. And that was designed by a Navajo artist for us. It was intended to, Atsa's, he said, was the eagle, and it's the symbol within there is covering the Earth, space, essentially Earth space sort of continuum. The colors at the bottom are intended to cover, although we added a little more blue at the bottom, intended to cover the spectral range that we can cover with the instrumentation. There's a lot of symbolism we built into it, and we love it, but you know, there it is. And go ahead. So my research interest, and I'll be really fast, I'm sorry to be going on about this, but I'm an optical astronomer. Go ahead. I look at largely, most of my work is based on surface composition studies of solar system objects from reflected spectrophotometry, which basically is the sunlight. It's a surface, it interacts with up to 1 millimeter of the surface material, and is affected by whatever the surface composition is, or mineralogy, and is reflected in the, when you take out the signature of the sun and look at what's left, it can be very diagnostic of the type of material that you're looking at. That's largely what I do. We get affected by space weathering, and we go ahead. And one of the things that I have done is identify materials that have been created by water and the accumulation of water or the effects of water on the material, underlying material that's been there, minerals, changing the minerals around it. It's called aqueous alteration, and I've done a fair amount of identifying some particular features that are related to that. And space weathering, or the alteration of surface material from whatever the environment is presented to you, is a problem for any type of remote observing. And if we do continue to do remote observing, we have to learn what these different effects are going to be. You know, we've proven that this is the case. We have ground truth samples from the moon. We have ground truth samples from the asteroid Itokawa that the Japanese brought back. And we can see that the effects of the space weathering. And it's largely solar wind driven, probably, but also can be micrometeorite driven. So we have to understand all of that as well. Mercury, in a totally different sense from my, the rest of this is all I do, largely very primitive materials, and then Mercury, which is like the poster child for the exposure to the sun within our solar system. And I've been I was on the messenger science team still in, and I've been working on Mercury's composition for years. That was probably my undergraduate and my master's thesis work. But I got sent to Chile too. So, yeah. So then I will tell you about Atsa, which is what the sort of long title is, basically. This was an artist's conception. If you know anything about telescopes, you know that the central, I have to tell us anybody who's astronomy, they're going to look and go, oh my God, they're looking at very small field of view, because the central telescope, this part is way, 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 way too small for what we could possibly do. We would have it larger, the secondary telescope would be larger in its field of view. So anyway, but it's otherwise pretty much honest. The point for us was that we want to site the telescope in the dorsal pod that XCOR is planning to put up on its Lynx 3, and we want to be able to flip that puppy open and expose it to deep space and look at things which will go into the best window is no window. So the part of it is, what's the advantage scientifically? We have the Hubble Space Telescope up there. We have had Spitzer up there, and we're about to launch James Webb, and we can apply to Sophia. And for all of these, the exclusion angle around them, this is what's unique to what we do. We can point this thing at anything that we want to point it at. But what can it do that anybody else cannot do, either from the ground or from space? These all have exclusion angles around the sun. Basically, if Hubble slewed across the sun and fried a whole bunch of its optics and materials, it's a bad day for Hubble and astronomers. And what we don't much care about that, because we're looking at this like an aircraft that's going up, essentially. We're not worrying about as much about heat shielding. We just don't point at the sun. Because, but if we do, we just land, replace our CCD or whatever our detectors or whatever we've heard, and just launch it again. It's easy, it's cheap, we can do that. Most objects are going to be fine for all of these other telescopes. Most objects, for astronomers, you wait 3 months, and if it's sitting near the sun, you wait 3 months, it's going to be far enough away from the sun, it's no problem. For some objects, particularly those that will be inside the Earth's orbit, you're going to run into a problem. Like asteroids, comets, Mercury, Venus, volcanic searches, anything else. This is not going to be an issue for any suborbital telescopes. Suborbital spacecraft aren't going to have a problem with this at all. That's what we're aiming for. 2 types of planetary observations can be done with this. One is what we call open field, where the field of view is what's important. Your absolute pointing is not as important as a reasonable field of view. But you have to be large enough to have identifiable stars in the field of view. You have to be large enough to be able to look in that center and say, yeah, okay, we know where we are. And otherwise, target-specific observations. You have to be able to acquire the target for suborbital flights. Acquire the target quickly, acquire it easily. You keep that target in your instrument field of view, like pointed really well. And both of these efforts, open field and target specific, are going to depend upon the magnitude of the target, coupled with the instrumental capabilities and the pointing ability. And I'd say probably pointing ability is going to be your worst problem with this. So there you go. Simple targets. Inner-Earth asteroids, they're pretty faint, but you're not going to get them from the ground-based observations easily because they're coming from the sun. You can't point your big telescopes over to look at them. And you can't point most of our space-based assets at them. We will, I'm sure, if they suddenly find a telescope for an object that's coming into here, everybody's going to look at it. But at the moment, no, that's not going to happen. Mercury, Venus, this is just a visual magnitude comparison. Okay. There's a rich history of observing objects in low Earth orbit, which basically is what the suborbital platform will do. You're above the water vapor at 100 kilometers. You can have access to a full IR range without losing anything in the way of transmission there. You avoid anything happening in the Earth's atmosphere at the time. For ultraviolet observations, which is probably even more critical because things like James Webb are going to go off and look at infrared stuff, so be able to open infrared. There's very little to nothing in the way of UV observations going on right now, except Hubble when they can. UV above the ozone layer, and that's open to UV to observers. This is something that you have to go into suborbital space as a minimum, even although we are only able to, in suborbital space, be able to, say, point on something for a limited amount of time, you're still above the Earth's atmosphere, and that doesn't even happen for, say, a living object. There is that difference. They have a concern with pointing and stability, and they're going to have a concern with the fact that they really aren't totally above everything there. So we're trying to do that. Right. So we want to do a crude CREWE. That's what it's a CREWE. Suborbital Observatory. And so the first thing to point out is that NASA has a long history of suborbital science. Most people don't care about suborbital science. Well, NASA has, and it still does. It launches a lot of sounding rockets from all of Simon, the whole Black Planet project. And it has produced a huge amount of great results. Also, however, you launch your Black Planet rocket, it goes up, and it's a hugely violent environment. It goes up, it makes your observation, it either does or doesn't do it, brings it back down, and theory you can reuse it in practice. It's probably punching into the Earth at pretty high forces, meaning maybe you destroy everything and it costs a lot of money. Yeah. Anyway, so the suborbital craft, it's a lower cost per launch. Really, in the end, it's going to be lower by a long shot than you could have a sun rocket. And you return the instrument in the same condition as it left, or if you don't, you replace it. You have more flights. Your objectives accomplished. And we have a larger telescope than almost any Black Planet NASA project has come up with. In your program, it's cost effective and reusable because it is reusable to be able to go with something like the Atsa, something like this. So anyway, I'm back to Lots of years, no big people. Technologically, yay. The next. We took some lessons learned from a couple of things. One is ground-based observatories. I talked about the MMT. Obviously, I'm going to put up a picture of the MMT. But in any case, we have two types of instruments in most ground-based observatories. Facility instruments, instruments that are maintained by the observatory. Principal investigator instruments, instruments that PIs bring to the telescope and chunk on the back of it. We conduct 3 observation types these days. One is observer tended. I go up to the telescope, I tell them what I want to observe, I've been awarded my guide to observing, and I conduct what it is in the sequencing of the observing that I want. Service observing. I get my observing time, I don't want to go up to the telescope or can't. The observatory offers a service where they will conduct the amount of time that you've been awarded, somebody can do the observing for you. Q observing. I've been given some amount of time, some number of objects, and how someone schedules this, fortunately, I never had to do it. Somebody else has worked it as magic, but basically one observer melds different people's projects into a queue and observe them. The flexibility to adjust observations or to guide or to interact with the observations is something that all astronomers want to have, even those who are doing observing for other people. Visiting astronomers, if they come to do their observing, they are trained on the in-house system. And any telescope has preventive maintenance that's conducted. It's just always happens. Airborne or space-based observatories, and I chose very purposely to show an F-18 observation where a person doing it, that's happening on CERN. Observations are really heavily scripted. You don't waste time. It's not possible. You have robust instrumentation because if you're doing it and you're up there, you're just not going to have easy maintenance. Particularly for something like Hubble or an asset that's up there for a long time. Maintenance is not easily possible. Any proposed observation, for example, I have just received in the last couple of days, some observations that I've been doing with some other people from Hubble. And our feasibility for doing what we propose is reviewed by a staff there at the Space Telescope Science Institute. If it's not feasible, you still go ahead and you potentially be chosen to observe. So you always review the technical feasibility. So we combine the best of all these worlds. If we're going to a suborbital platform, and we came up with Atsa. And Atsa is a facility. We want to make that very clear. It's meant to be an observatory. It's a facility. It's moving beyond just doing a flight or flights. We want to maintain a telescope or ultimately telescopes interchangeably with the freedom to attach to different instruments. We'll have facility instruments. They're available in-house. We'll have principal investigator instruments. We can slap them on the back, provided by the observatory user. Data storage will be on board the flight, so that we don't have to download anything, and we can just bring it back and unload it. And the operator can be a guest observer, or we'll do service observing, one or the other. But we're very easy on it. The whole point was to do it as a facility, not just something that's more individually focused. The same thing, contributions, we took some things from ground-based and space-based. Ground-based observing, we have 2 types of observing that we want to conduct, observer-tended or service observing. We're flexible, you can adjust observations, you can go up, take a look at something and say, hey, this doesn't quite work, go up again, and then adjust in how you're going to do it. Visiting astronomers will be trained on the in-house system, and periodic preventive maintenance is obviously effective. For space-based observations, observations are very heavily scripted. We have robust instrumentation in mind, and we review the technical feasibility of any observation that's being proposed. So, using X4 links, which we hope will fly in the next year. The transmission on the spacecraft, the best window is no window. Ultimately, the X4 Lynx 3 has a dorsal pod opening to space. It means that nothing is going to be blocking the telescope from what it is you're looking at in space. That's a big deal for us. Pointing accuracy as published by X4, the Mark 1 is plus or minus 2 degrees. Mark 2 and Mark 3 being the equivalent of Mark 2 with a dorsal pod, is plus or minus a half degree. It's great. Our pointing, which is our biggest challenge, is a balance between the coarse pointing of the spacecraft will offer. And the fine pointing that would be conducted by a human operator. And we would publish a list of criteria for a PI instrument they'd have to meet before they could fly on Atsa. We would review a project technically for feasibility and make this a smooth operation for anybody who has their own instrumentation. Right. So what I think fiscally, it's the next part of this. Basically, your observing program, a person's observing program would be feasible, adaptable. You can tailor your future observations based on your previous results. It's not as expensive. We cut out redundancy in instrumentation because we're landing, so if we heard something, we can fix it and put it back in. A reflight establishes a cost savings in the repeated use of the same instruments. Onboard data storage moves downlink expenses. The actual flight costs themselves are probably cheaper. And the standardization of observing removes the cost of duplicating efforts from many observing programs, allows the astronomer to tailor the program as they want to do it. And if you want to do surface observing, it's it. So what does this mean to you if you want to be a suborbital observer? Right. You want to acquire an astronomical observation now, sooner or later. And we will check it out. Can we do it? We'll run your proposed observation through our simulator. We'll tailor the observing sequence and we'll simulate the expected results and give you as hey, this is going to work or it won't. Right. Okay. You want to do the astronomical observation, you want to do it yourself. We'll send you to Atsa specific FAA approved NASAR training for observers with our telescope. Okay. And we've done it. We had the first Atsa specific NASAR training session back in 2011. We're actually hoping to return probably sometime within the next few months to do another one. That's us, or at least some of us. And the only person not smiling there is my collaborator, Luke Saul. It's way too somber in the middle of it. I don't know why. The rest of us, of course, are all, we have students. Now, this is an important aspect of our project. A lot of our participation in projects and design has been done by students related to the Citadel or South Carolina Space Grant. And these are various and sundry different students that were there along with me, which is not a student. So then we have pictures of Luke undergoing G training and students, and Luke always likes to point out that what doesn't understand why 19-year-old students don't look like they've aged when they go through like 6 Gs, but he does. So I can find out why. But, anyway, go ahead. So anyway, you want to get an astronomical observation. You don't want to go anywhere near a flying Toucan. We'll do it for you. Go ahead. You want to do an astronomical observation. You want to fly your own instrument with our telescope. Same thing. Give us the specs. We'll see if it's feasible with our telescope, and we can shepherd it through any regulatory processes that might come up. Our long-term hope is to have the Atsa 2 telescope. The Atsa 1 camera is what we're hoping to fly now to test our tracking, pointing and tracking methodology and see whether we can, how close we can point to the sun. The Atsa 2 telescope will be 27 inches in diameter, larger than anything that's going up right now on thank you. Somebody figured this one out. And this is the type of instrumentation that we'd like to put on board. Go ahead. The Atsa 1 camera is our engineering proof of concept. That's what we have developed at this point. We want to test the idea of acquiring and tracking a target from the suborbital spacecraft. Can we do it? We will be looking through glass or these windows. At this point, we have done the testing on the transmission windows, but we're only looking invisible at this point across a particular spectrum. The requirements that we need to design and build to, essentially were there. Typical lows of 3 to 4 Gs. FAA certification issues. We cannot impede emergency egress from points. That was a biggie for us when we went out to do that testing. And we must be able to wear a suit and suit gloves and operate the whole thing with the suit gloves. We want to use off-the-shelf parts. We've done that largely. In a couple of cases, we finally realized we had to sort of design something that was, or adapt something that was off-the-shelf for our use. Most of this has been developed by an undergraduate student team. Like I said, one of the objectives we have developed as part of this, and in particular Luke is very interested in this, is to ensure that undergraduates will always be involved with the operation and the flights. and the design and anything else that we do. Kirsten, because in some ways they've been really, really, really good at it. And it would be the type of situation in his mind where if you went to college and you majored in physics, say, and you got really good grades, and you could work on this project and you supported the project that maybe you fly in space. And if somebody had offered that to me, I'd be doing it so fast, it would be fun. I've not even gotten good grades. Anyway, that is his hope, and take it further than just the city health. Right now it's at the city health.
And he's gonna give new meaning to space cadets, right?
Yes, exactly. Yeah, it's not limited anymore at this point. This is right now what we have. An old side-band camera. It does work though, it's ruggedized. An FLI 5-position filter wheel. We have some 2-inch narrowband filters. We picked them so that we can get some science out of our initial flights in any case. Both chemical observations of Venus's cloud covers at different locations and maybe Mercury as well. Plus our field range 3.5 LW ruggedized Matsukoff casting telescope. That's one that we had to have. We fixed, ruggedized, tinted dark. It has a field of view of about 3 degrees. Our total weight is about 8 pounds, which doesn't sound like much, but it can be a lot when you're going at 6 Gs, or relatively speaking. We have a, those are the filters. 4 or 5 of the filters will be used for the Mercury surface reflectance Venus atmosphere transmission. And go ahead. This is an old drawing, but it's very similar. Mechanical system that has mounts to a step hinge. We called for a while the Atsa armrest camera, the Atsa lazy boy camera, but it's now the Atsa one camera. And we would have screens and we steer by hand. We have the fluid head camera mount, which works very well for this type of system. So that, and it attaches to a hinge within the lens itself and looks through the mirrors, or I'm sorry, through the windows in the ceiling. And that's just more of the cartooning fluid head. If you take up the 8 Gs, we have a lot of margin. It mounted lots safely for takeoff and entry, and we have no commercial electromechanical gimbal that would accommodate that. So it's either too large or too expensive for us, and we did it this way. So, go ahead. That obviously is sort of an idea of, yeah, it can work. Yeah, we have room for egress. It's out of the pilot science side. We're not disturbing the guy who's flying the plane and things everything back. And that was the old configuration, which is just there. We do fit. And go ahead.
And you can get in and out
With
with that camera right there.
That's right. I probably was the worst at it. We had a safety person from Export come out and take a look at us when we were there at the time, and he pronounced this very, quote, very uninteresting from the safety point of view because we couldn't fly. Right, that's exactly where we wanted to be.
Well, look, I have a question about that. I
Sure.
can see that the pilot has no trouble getting out, but your equipment operator might be a little bit encumbered. How do you feel about that?
Actually, almost everybody can, it's the only person who had trouble pulling this off was me because I'm probably older and greater. But everybody else had no problem with sort of pushing themselves up and sliding out. And getting out. It was a very pretty easy process. I probably could do it with some practice. They were doing it a lot more easily, especially the kids that were in college at the time. They could do it really, really well. But it's still a real problem for almost everybody else who's doing this. And so it looks more difficult to me, but we practiced it a few times. We had to demonstrate that as part of it. Being very uninteresting. We have to show them that we can be okay. And that's just us. And guidance and control, I'm not going to go through a lot of that. We need to find out where we are in the sky when the telescope turns on. We have a system that searches the space constrained to about 5 degrees around our coordinates that we want to go to. It allows for some pointing accuracy, and then it shows us where to point to. And an arrow points to where we need to guide it to, and we can supplement this with a chart underneath. But the idea is to test, and this is what we want to test. Can we really do this? And if we can do this, then we'll go for working on the full telescope. If not, well, then I guess we're not. But so we developed a whole, baseline. We read the science floor, we read the baselines, all of our objectives on that our test program. We had a suite of 11 flights planned, and what's required is what we had to meet was the red Number one, survives launch, it survives landing, we're happy. If we can do other things like unlock and maneuver the, we're very conservative on this one. Unlock and maneuver the telescope and acquire imaging data even better. Can we get some images of Venus? We were trying to get images first of Venus at greater than 42 degrees of elongation from the sun, and then try to get multispectral images, and then repeat that. We repeat everything at least once. Images of Venus when it's closer to the sun, Venus being bright enough that it could do that. Repeat it. Images of Mercury at greater than 20 degrees. Mercury never gets greater than 28 degrees from the sun, so it's a hard thing to observe from any place unless you're in orbit around Mercury. And repeat that. Then we're trying to push Mercury to less than 20 degrees and just see how far we can push toward the sun with it, and then see if we can pick up something else that is even smaller. But these are our test objectives. Flight planning and training. The period of time above Earth is really, really short. At all times, very heavily scripted. If you're going to be doing this, you need effective time management. It has to be critical to mission success. You got to practice the whole thing. You don't waste time. And so we want to set up the mission and practice them beforehand before people go. And human factors. I was sort of poo-pooing the NASAR training because I pulled some images in other situations. I came away from the NASAR training thinking this is a really important thing to do. For a lot of reasons, it's really, really quite good to do. G-loading training on that humid centrifuge, in the configuration that we fly ultimately was really worthwhile doing for somebody. Hyperbaric training was kind of nice, but what the hell. Distraction factors that we're not going to have any tourists going by, distract you, but we went through some of that. The goals of the training are really to provide hands-on experience to aid in this design, and it has really helped our students when we send them through this. We usually send the students to the NASAR training that we have right now, or they have right now for scientists, so they can understand what they're dealing with. And the result of one of the rounds of the NASAR centrifuge training was that we abandoned the electromechanical gimbal in favor of the fluid head mount, which is why I mentioned it a couple of times. And we consider this to be a necessary thing for any future operator. So we've worked on this since 2007, sort of where we are now. We've talked flight orientation and positioning and reviewed this with export. We've opened discussions of requirements for mounting the telescope with links 3 dorsal pod, sort of waiting for further definition of what their internal characteristics are going to be. That probably, and we have started talking to people about the design of the final telescope. But really, that's going to depend upon what our results are from our first round.
That's fine. Looks like later.
Yes.
Less than 100.
Mm-hmm.
Who knows? Wow.
Yeah.
Mm-hmm. So that was our objective. Yeah. Anyway, and so I think, unless I go ahead. Oh, including thoughts. It's a practical system. The first version of the observatory is built, essentially. We're doing the last couple of bits of testing and waiting for export to launch the phase 1 and seeing if we can put it on board. Plus, I'm learning how to knock on doors and look for money. I'm not so well skilled at that, but I'm learning really fast. We have research scientists from PSI, Planetary Science Institute. We have the students. They have been an integral part of this. They remain an integral part of this. They will probably fly. We plan for them to fly. We want them to fly the first student in this case, and the user community. And we're sort of hoping that we'll be ready to fly because we'd like to do some more testing of shake, rattle, and roll. A little bit of testing, human factors testing. We asked somebody to respond very quickly to as soon as they have launched in space, they have to start operating the telescope. In fact, with the shuttle, that people did not do a lot of work within the first few minutes that they were up in space because they just wanted to let them adapt to it sort of initially. And I confirmed this with this one shuttle pilot. And we're asking people to immediately operate this. And we want to test to see whether that's feasible. We have at least a proposal to do some bring back his testimony on to see if that's going to be that we cannot do or could we do. And then we just wanted to finalize the design. The function test we could do from in this very shortly, if they'll let us go through the spacecraft anyway. And yes, I think that's it. Thank you. Questions, or if I can't answer the question, then I'll be happy to research it more for you.
I know the test version of the telescope using a max telescope grant. I know you haven't done the tests yet, but is that the design you're anticipating for the flight version?
Potentially, maybe the Atsa copy.
Uh-huh.
I'm not sure how we'll end up being for the final version. We haven't even gotten, we started talking to optical engineers about what could fit into the dorsal line, but we haven't gotten to design that because we want to see what's the first.
Nice.
I have a question. Thank you for your presentation. And you mentioned the targets, the planetary and the asteroidal, and I was wondering if there's any sense of specific kinds of research questions that we'd like to answer with ASCEN.
The ones of what I was talking about with this were questions that were specific to what we could accomplish that was unique. And so anything with ultraviolet, and we've had people approach us who want to test detectors in ultraviolet on any sort of target, any target that's temporal, and that is not limited to regular or to planetary sciences, regular astronomy. We can look at anything we want to regular. The moon, in more depth, although I don't have my computer with me, we can look at different aspects of structures of Venus's atmosphere and temporal changes, which are things that are not monitored after a lot of the spacecraft will go by and we'll do monitor them from the Earth. We can also monitor them from space and probably wavelength regions that can't be seen from the Earth. And there are people, we talk to people who are being scientists, which I am not one, so I'm not going to be able to talk to you about that. Mercury, I don't know how much in the way of uniqueness we're going to do in the visible spectral region, maybe some, but we can at least confirm the surface composition of the reflecting spectroscopy of the surface composition for the planet, probably not enough resolution that we're getting with something like Messenger, but, and this is something I do know something about. If we can confirm what they are seeing, we'll have some spatial resolution to this, even as a first round of observing as part of the Atsa one project. That would, at some level, that's going to confirm the efficacy of the project for being able to acquire data. There's very little that you're going to see in Mercury at the lower spatial resolution than the advanced spectration. I know because I've done that for like 40 years at different times. And it's been something that everybody critically would find some of the traces of iron oxides on Mercury's surface composition, because it makes a lot of sense to see iron on Mercury because it's so heavy, it's massive. And they just assumed that the problems were that we were observing this through Earth's atmosphere very thickly with the surface and not wanting to see that. And then we got to the Messenger and discovered, guess what? The signature is not there, which is something that I had predicted many years ago. And went to see myself disprove actually. And was happy to see the happy. I like the fact that it backed me up. Yeah, I did it right here stuff. But it's we can confirm what we have seen already. As far as looking at say, Earth or sun grazing comets or something like that, we can also take a look at comets as they approach closer to the sun, which nobody else can do this in the aerospace sense. We have the chance to look at things when they're closer to the sun and will be outgassed and affected by it. Ultimately, I think there are a lot of people who still do a lot of the sun environment observations of things like atmospheric properties of some of these planets. And then that's something that we can do really well, I think, with the final version of Atsa. But the first version is not intended to be as much to do anything of it. I think we can get some good science out of Venus observations. I think we just confirm the science on it. Yeah. But you can kind of do it. You don't have to find the process. I'm going to find all the way in a different direction, as far as that goes. But the gamma ray burst, or you need to get something that was a little bit less. Yeah. But, this is what's unique to what it is, the UV observation is unique as well. I don't know how that's.
Yeah, thank you, that's.
Sir,
Yes, how are you gonna do UV and Viz and IR?
individual flights.
Individual?
The UV observations probably would be separate than visible spectral region and VNIR. Same
And you're
with
all dependent on flying on export.
well, they're all dependent on flying in suborbital space. X-Core we identified as being a really good candidate spacecraft, and we focused on X-Core because of the pod, because it has the opening into space, the best one is that window. We don't want to look through anything we don't have to look through. And almost every other spacecraft that I've run into requires you to look at through something. And even if they're going into orbital space, the suborbital, the advantage to X-Core that we saw was the pod. And I don't think it was originally designed to have a telescope in it, but we just looked at it and said, we can use this, So,
One other question.
Sure.
Vis-a-vis Sophia.
Mhm.
I understand Sophia is much lower and got more atmosphere, but it's got a larger aperture.
Right.
So.
Sophia's fantastic the way it is located. It actually can point to within about 20 degrees of the sun. It's designed to do that. It doesn't go up through the full atmosphere, but it gets above an awful lot of Earth water, but it only does IR observations at the moment. And that's all it's planned to do, as near as I can tell. I don't think it does visible, and it certainly doesn't do UV visible.
Which have a focal plane?
They're not allowed to, I don't think. I mean, one thing that I'm watching, and I've not observed with this Sophia, I admit, is how well it's working. I hope it works really well. I'm not thinking it's necessarily not going to. It took a long time to get it online and to get it working. A lot longer than we expected. They decommissioned the Kuiper Observatory at the beginning of the 1990s in order to be able to get Sophia up within a year or two. It's taken until maybe the first decade of the 2000s has passed. So it is centered on, focused on infrared observations. I don't know how it's going to jive with James Webb. I kind of hope they keep it going because the more assets, the merrier in my book. But there's a cost factor involved in refitting it to do something that it's not designed to do. But it is designed to get the IR observations and to be able to push further into the IR than we are planning at this point with Atsa. I find it complimentary, actually.
The X-15 program is similar to the Lynx in terms of its performance. They only had one pilot on board, but they were doing scientific experiments in that configuration. How many seconds above 100,000, 100 kilometers, do you expect to have available for observation?
With the final Lynx version, usually have 35 minutes, if I'm not mistaken. And that is going to be shorter than you're going to get the time-wise for one of the Sonic rockets, which like Dr. Ramsey to push higher.
Yeah.
But we still, if you can piggyback 2 or 3 of them, we get a whole bunch of doing at a time and cycle your instruments.
Are you sure Lynx is saying that? Because I think that they're aiming to just raise the 100 kilometers, not actually spend any time up there. They don't have any propulsion capability at their maximum output.
I think they were planning to, I think that was what we had been told, that they were expecting to get there for a certain amount of time, but you can get up longer with a higher, if you provide to go higher. No, they're not gonna go a lot above 100 kilometers. They're limited time-wise. But I understood it was 3 to 5 minutes. So take it 3.
Yeah, I think you guys remember they're in ballistic trajectory, so from their perspective, their cell is the weightless time, because that's what they want to tell people that you're being an astronaut. So that the engine goes off, they're weightless at that point, but they're nowhere near 100 kilometers.
But they're going up to 100 kilometers. That's what we
Right,
did.
that's
I disagree. My understanding is not that they're gonna go up and drop. That's not, maybe I'm wrong. Maybe I'm wrong.
Well,
I don't know.
burnout,
purely ballistic.
burnout is different. Burnout time is different from time above the atmosphere. That's correct.
Right.
Right.
I'm looking at that. That's sort of
We
important.
will, but we have
Yeah.
looked into it too.
Okay.
We thought we were going to do it that way. We're not constrained to only working with X-cores was the handback. But my understanding was not that it's just going up and down and just physically 100 kilometers and dropping. But we were not going to get a lot of it for a long period of time. That was not the objective. We didn't do that. And we aren't going to get that for the Lynx one. So we're only going to be able to test that one. We thought we had about 50 seconds to prove whether or not we had, the stuff to be able to point to track on a wider object. That was what our game was not. We're not expecting 35 minutes at all.
That's actually, this is so brings my question. Because you have a limited time at the altitude that you want, how do you plan on maximizing the use of time? Like you alluded to it earlier, you want people to start immediately as soon as, yeah.
As soon as we're done, all you have to do is unlock it. It should be if the Lynx can point to within, say, plus or minus a half a degree, our telescope will be able to point to within that particular region, and we have a method by which we have been developing and testing, where we can look at a field of view, and we know roughly where we're pointing. We've given them the order. We want to be roughly here, and they should be able to point roughly
It's
here.
a little bit like Sophia. I'm thinking like how they have an area, not to compare obviously, because it's not just like something that is not just like a fountain fruit, but I know that Sophia's had some problems with her computer systems crash or go down. And
That's why we have a person who did it.
yeah, I was like,
We have a much simpler
I was
system.
like, if you have this limited amount of time as you have, like that is not an option. How do you plan
That's
on
the
making
point.
your systems robust?
That's why we're testing it, and we've already been testing it on the ground as well.
Mhm.
But that's exactly why we are testing it. And if it doesn't work, it doesn't work. Then we know, and we haven't spent a lot of money building something huge. But Sophia has the advantage of being able to continue to fly.
Yeah.
So they will find what they need to find.
How scalable is it? How many flights do you think you'll be able to accomplish in a year? Do you think you can build additional observatories that could fly in parallel?
I think X-Core's, if we're using X-Core's original thought was they could take off, fly and land possibly up to 4 times a day. Let's take that as we figure we could potentially fly on each one of those if we wanted to. With one change of configuration would be a greater problem. It's perfectly scalable to be interchangeable. The issue there is if we can afford to and how much we can get in the way of instrumentation to fly. The idea was to be able to change it and to be able to use it on short notice. There's also a question of course, we're limited to location for the particular flight. So if we want to get something that somehow is specific to, say, Florida, and you're sitting in California, then you've got to get your instrumentation to Florida. There are questions of that involved. But I'm not worried about repeatability. If it's a go for pointing and tracking, which is the most important problem that we've got in my book, and we acknowledge that, and that's what we're trying to test, then I think it's no issue as far as the instrumentation goes. I imagine there's a shape out there about looking at the aspect.
So are you saying the telescope and the optics can cover UV through IR? You just have to swap out the back end for a different vision?
We can have 4 optics telescopes that are optimized to UV versus IR as well. It's
So
intended to be
that's
very
all
modular.
Modular.
We're not looking at this as being only one telescope. We're looking at it as being an observatory. We're looking to tailor your observations to what you need. In the case of the person who approached us about doing potentially testing of UV detectors, we have probably the same 4 optics and be changing out the detectors, whatever the detectors are, no matter what. In the case of IR observations, I don't know that we're going to go into anything where we are thinking about cooling anything, but cooling the whole system down. But it's a short observation, and it is a short amount of time. That's what people have said. We're hoping to make the whole thing pretty interchangeable. We'd like to fly first and test it, the concept, but the idea, our mental idea was to make this not just a one-shot deal or a limited shot deal, was to make it what people need and can use, and to make it augment somebody else. Yeah.
So I noticed you said that somebody approached you regarding UV research. Are you guys taking private payloads for people to experiment or?
Oh, yeah. Yeah, we're not limiting anything here. In fact, absolutely. We're trying not to be constrained by, I'm trying very hard not to take NASA money for this, so that I'm not required to have to wait a million years to be able to launch it, and then have to build in that huge redundancy and a whole bunch of other things like that. But yes, that's the whole purpose of it. If we take whatever's going to work with the system, and won't cause any danger, but, work with the system, yeah.
Why do you need a person on board?
We eliminate a lot of the redundancy of instrumentation, but otherwise we can get the work we can do very fast. Adjustment of the observations. We cut our cost tremendously from there. And what the heck difference does it make if it's a lot cheaper to do such a thing, and you don't have to make it as complex an instrumentation? Why not have a person?
The way 200 pounds, it's about 10% of the, it's about 10% of the whole mission.
But that's what the whole spacecraft is intended to do, is to fly two people, effectively.
And the FAA, what are that officers?
Yes.
The regulatory issues are just going to be nasty.
Unfortunately, they're probably going to be a lot nastier now than they were 6 months ago.
So could you eliminate the person?
No, we have no chance to make any adjustment. Then we might as well go back to sounding rockets. Then you have to have redundancy in your operations, redundancy in your planning to be accurate in the planning. You have no chance to make that as a correction. The objective in this case was to make it a more flexible system. And flexible system is sticking human.
It's not your particular mission plan, but if Explorer really wants, their advantage over the sounding rockets is that you don't throw $1 million away each time you launch.
Right.
You replace all the pilots, that's 500 pounds at least of environmental, the people themselves and so forth. That's a lot of payload. And all it takes is an autopilot and a radio and an RC controller. It sounds like if it works, it sounds like a possible idea for things.
Everyone's into it wrong.
Yeah,
That's
exactly.
how high drones can go.
It's you can remotely control things on the moon, so it's actually, that's not a problem. But that would give you a whole lot more mission, it seems to me.
That I will give up to the expert.
Yeah, exactly.
And I think we will.
So a key interest of Atsa Suborbital Observatory seems to be planetary composition.
It's what I do.
Many other things too, but that's a key interest, right?
That is my interest.
And my question for you is, what would you say when you're looking at Venus, Mars, Mercury, what are the biggest gaps of knowledge in terms of the composition? So if you had, if you could find out a little bit more about either something in the visible spectrum or UV or IR, what is that kind of data range that you think is really missing? That worth $64 million data range. You can find that.
For Venus, and I will go to Venus first because to me it's a very obvious thing. We've sent spacecraft to Venus, but I bet you we'll send another one in the near future. I'm just banking on that one's being a like target for NASA, something the Discovery program maybe. For Venus, we have temporal observations that are not that for which changes in the atmosphere values. I'm not an atmosphere person, so I'm a little bit apologizing for this. Are determined both the visible and the near infrared, and also the UV. And the temporal observations, they change on a day-to-day basis, they change on the way down to the surface. We don't know much about the composition of the surface material yet. We don't know much about how Venus's atmosphere is going to respond in periods of time. Getting a sweep of observations over a period of time and being able to observe them repeatedly is going to give us that type of information. For Mercury, we even have less knowledge of what its mineralogical composition is than we would expect to have had after the atmosphere has left. We have a little more than maybe less in some ways than we did before we got to Mercury, because we were expecting a lot of iron oxides that did not appear, maybe silicates, Pearson's oxides, things like that. Because the iron oxide isn't there, the iron isn't there on the surface material. We determined that from the elemental composition experiments on board the passenger. They've given us a good idea of what materials, elements are, some of the elements out of there, key mineral forming elements are there. But it came as a surprise to us to not find a lot of other things. We're probably going to learn the most about the composition of mercury from, say, mid-infrared. And that is something that maybe we will not do with Atsa. That's something that I expect the European Benthic Formal Mission will do. And they are doing laboratory work to back that up at this point. The elemental experiments, X-ray fluorescence, gamma ray fluorescence, neutron spectrometry, onboard messenger really gave us almost major clues as far as composition goes. So probably, however, there is a change in Mercury's atmosphere and atmospheric components that can be observed from the Earth and does vary with time. And Mercury has an exosphere, essentially, so it's a surface-bounded atmosphere. And that's the type of thing that you would want to be able to look at and observe how it is changing. There are things that are driving it that we now understand are driving Mercury's attributes, like a very changing magnetosphere, magnetic field that are even offset from the actual physical equator of Mercury. And I mean, way too much of this. That we'd like to see why and how they are affecting this. And this, again, Bepi Colombo is scheduled to fly to Mercury at this point with the European Space Agency. I expect that to produce some results. Mars, everybody loves Mars. Everybody wants to observe Mars. Mars is just amazingly productive material from Mars. And I don't expect really that we're going to learn a lot with Atsa concerning Mars, frankly. I think that's going to come from a lot of the ground business. But I hope that answered your question. I think things like comets going to and around the Earth, near the asteroids, there's a whole suite of them that are very difficult to observe from the ground because of where they're coming from and solar interference. You could bet if, again, as I said before, you could bet if we discovered there was something that was coming that was really going to hit the Earth and we had time to take a hard look at it, we'd be turning every asset that we have toward it in that very culture. You had a question? No? I'm sorry.
So, this is a question regarding data. I noticed in the presentation you wrote that data will be collected on the link itself.
Mm-hmm.
So,
in our own computer that's located behind in the location behind the operator.
And if you know the USA had affiliate and they would just send information back to Earth. So what was the reason behind keeping that data on?
It's a lot cheaper and a lot easier to keep it on board the spacecraft than to send it back here. We're not dominating anything. We're not trying to set up anything that's going to dominate. And we can just keep it. It's again, we were trying to do robust, but off the shelf and not expensive. We're trying to make essentially the move toward a commercial space ISO, or at least a scientific asset that's not terribly expensive, doesn't require as much. So the idea was to store the data on board the spacecraft. When you land after your 5-minute flight or total 15-20 minutes, you just walk out and you're there. So that really was our objective. We didn't have to dominate anything. We didn't have to have an asset up front that received the data. We didn't have to organize that.
Quick one. Is it thought that it'll fly out of Johnson, or where is that? Where
I wouldn't find out.
okay. Or where?
Well, if we're tied to the Export Aerospace company, I think they have launch sites planned at this point. I don't know if they're planning to keep Mojave or not, but right now they're at Mojave. Yeah. And then they have West Texas and Midland, Odessa, and I think they just bought some property at the Cape American Space Center, and they're trying very hard to locate, I think, in different locations with the intention of being able to, I don't know if they're planning to move spacecraft or have multiple spacecraft to fly, but the idea was that they're
It's like LiDAR in space or something.
yeah, there's a lot of different locations that we can fly. So, we'd be tied to what they were having, but that they move their asset to different locations, maybe, I don't know. Anyway, that's their business. That's the thing. I don't have to design for that. I'm happy to design. So,
markets. So what you're looking at is some markets and other
astronomers, people developing technology. let me make a general statement about how it would be pointed to space, we can also point down. And we had some people who expressed interest in the need to look down, as well as up, you know. But our background, of course, is within, astronomy. So our
So is that like universities? international
universities,
agencies?
sure, universities, federal agencies, anybody who wants to and can buy.
Since you are looking at your objects and asteroids and so forth, I think some of the new companies that are interested in mining the asteroids might also be customers.
Yeah, sure.
I
don't know,
haven't
I'm
talked, I haven't talked to them, but it's not a bad idea.
Yeah.
I know I've talked to, I can't think of the last name.
Deep Space Industries,
Yeah.
Planetary Resources.
Hunter, and I talked to this, really about it.
So with your business model, would you take the independent observations,
Sure.
commercializing the data, as well as selling the observatory services?
We'll take independent observations, we could do that. We can do whatever we can do, we'll be happy to do it, but if the person comes along.
You know, copyright.
Well, once we record the data, if somebody has come along and said, we want to do this observation, the scientist doesn't want to have to give the data to me. And I don't want them to have to. I don't want to use it the way that the telescope would use it. It's their data, it's our facility, if they pay to use the facility and using it, we are successful. Right. So no, I'm not requiring that data must go, you know, that you must own the data. But if I hope that answers the
So for
question.
your independent observations, you could then have.
Sure, yeah, because we're scientists too, yeah, so, yeah.
So what would be the cost to do an observation?
I don't know what the final cost is going to be. I think our current guesstimate at the cost of flying with the Lynx one is about $100,000. And that varies, that covers a lot of things that are support for the launch as well as the launch itself or the flight itself.
Is that what the customer would have to pay?
There's no customer that on Lynx one. That's all testing for the I don't know what it's going to be. I really just don't know. I think it'd still be, I'm guessing 100, 250,000 maybe.
Well, on Mark 3, I mean, it would, anywhere from $500K to $1 million to essentially fly Mark 3. And tell me, add your costs on top of that.
Our costs weren't included where their costs were, right? So we don't really know yet. It's going to be, if they fly it successfully repeatedly, out into the cost potentially drops significantly. Who knows?
Last year, or in the last 10 years, the average is about 19 launches of sounding rockets of all different capabilities. You're in the lower end of that capability market. Have you done any research on how many of those 19 launches would go Lynx and how many more the customers might pick up if the price were at your price point?
It varies. We have tried to do some research into that. Part of the problem is we don't always know what's on it. We can't find out. We haven't been able to find out what's on the launches. Some of them are scientific and we know about them.
Right, yes.
And actually there are plenty of those that would easily switch to Lynx, or they could be switched to Lynx and they want to do so. You know, things that
The performance was that.
that performance would work. Some of we tried very hard to find out what the manifests were for all the sound rockets for exactly that reason. We wanted to find out if there were customers, what we really wanted to do was find out if there were customers who might use Lynx and would be interested in supporting the testing program.
Yes.
And that we have not yet been able to fully do, find out. We do know the scientists, but they can't afford the testing, the testing program. So. But industry, there's industry, that somebody who would want to use such a thing, we would love to find out. We don't know, we haven't been able to do it. It may just be that we don't know how to work. The question, sir?
Pursuing this line of the commercial aspect, what would you do more of or less of to make yourself more commercially viable?
we're intended to be as commercially viable as we can be. What I would do more of on a personal level is find out the people who would be interested in such a thing and why they would be and how we could tailor it to them. If we can do an observation that will help somebody, then we would like to be able to do it. You know, frankly, a good chunk of my time in my career with NASA was spent designing space-based observations for meandering debris, low Earth orbit, geosync, and geotransfer orbits, and both assessing the environment for orbital debris and what could be done to protect, say, assets at geosync would be, I think, a very useful thing that we maybe could do to take a look at. And we've had one or two people approach us about that as well. We're not as heavily at a point of knowing what we can do with LIMS 3 as maybe we would just love to be. But I would try to find any aspect of the facility, which is what it really is, that would be useful to whoever would want to use it.
So you call that facility?
Right. An observatory facility. It's not intended to be somebody's, only dedicated into science straight. Observatory.
Any feeling as to UV is more important than this or IR? Any feeling of that space, what's important to him?
Only in that things like the UV would be almost unique for something like this, where IR is being done with Sophia, with James Webb, as far as our world goes. Hubble does UV, but it's limited. Of course, it has to do everything else as well. And Hubble is not guaranteed to be there forever. If it fails, it's the end of Hubble. So that's why the UV is important, because anybody who wants a UV observation in any direction would be useful. I guess when I sell this or when I present this, I'm presenting what I think this instrument suite or facility could do that's potentially unique as to it, or close to unique, as opposed to everything that it can do. It could do visible observations in directions 180 degrees from the sun, and it would be very happy. There's a lot. I happen to like to look in the visible spectral region. I've also done a lot of UV work lately. I've sort of backed away from the IR because everybody's jumped on the IR bandwagon, and I tend to look at it. But I have no reason not to pursue any spectral region that we can access adequately. I think for something where we have to cool the instrumentation sincerely very well, I think that would not work as well. So I think that's probably that would probably be. So.
You mentioned monitoring the orbital debris.
Sure.
And I think the U.S., the space community, U.S. in particular, monitors something like 22 to 25,000 objects, somewhere larger than 5 centimeters, mostly larger than 10 centimeters. And I've heard some estimates that Kessler syndrome, the cascade debris event, could be a real.
Kessler syndrome?
Kessler syndrome?
K-E-S-S-L-E-R?
Yes, I believe.
I didn't know Don's. Okay, that's cool. I worked with him years ago. I know he's retired. I'd love to see him, but I just really think that's very cool. That's very cool.
Okay, so I've heard that could potentially be a reality within 20 years to up to 50, possibly 70 years. And what's your sense of that risk as an actuality, and what types of consequences would you see that having for endeavors such as the Atsa Suborbital?
The issue with the Atsa, I think, largely would become, because it's so limited for the amount of time that it's spending in space, that the chances, the probability of it being affected by something that's significant as far as orbital debris goes, and also even at that altitude, is probably pretty limited. I mean, it's not spending a lot of time in space. You go up, the exposure and down is time temporally is very small. My understanding, although I don't think it's uniform, but my understanding is that a lot of international cooperation has now started to filter into deorbiting large rocket bodies like they can burn up, expending fuel from third stages of rockets so that it doesn't cause an unknown exposure, which is then going to cause another issue. And that the population has built but is not moving to a major level at this point. They have tracked, or at least they have, and they certainly have models for it to bring down to very small sizes that are lower than 5 centimeters. I thought they pretty well counted a good portion of the 1 centimeter population as well at certain altitudes. I think one of the issues is degradation of space assets from small materials, and then that, of course, snowballing. And beyond that, I'm sorry, I know what they're doing. I just think I haven't seen Don in many years. I was in that group, his group for many years, working with the space-based detection capabilities in the late 80s, early 90s. And I just think pretty highly of Don. So, that's cool. Hey, you're going to listen to him. See that. That's cool. But I don't know how to assess it. I think it's more of an issue of, I've always thought of it as an issue of real estate. How much can you put up for geosync? And what do we do with the objects when they're out of geosync? We move them off to some area where it's not a problem or where it can be. And degradation of surfaces as you get down into low Earth orbit, or those sorts of things like erosion of materials from something that's smaller.
I guess I was thinking about the potential to interfere with actual observations.
I was just actually about to say, the other thing is that potentially they're looking through observations. I always think of that was what we were not considering. But yeah, the more stuff you look through, the less reliable.
Pardon me. So suppose Explorer flies, and they fly at Atsa, and this is a huge success.
The first round and the second round are both.
And what next?
I die happy.
Okay, but for
seriously.
my kids,
I think that I think Atsa will continue to, it's a facility, hopefully it will be used. There's no limitation on its use. If your kids want to go to school to fly in space, we would be happy to incorporate them into a working system where we want to incorporate students. There's an educational aspect to this that we've had and we want to grow. In general, when you're talking to kids, if you're not talking about it, just sort of what happens in the future. And here I'm just getting theoretical and maybe hopeful as well, and with respect to both X4 and with respect to anybody else. I think that commercial space, I think that's the only way that ultimately the United States is going to be able to go. I mean, you are getting philosophy. You are not getting anything that's based on any serious bit of facts at all. If we don't go into commercial space and if we don't turn things over from NASA to commercial space and commercial space doesn't survive, I think we lose our ascendancy, essentially our supremacy in space, or our very, very strong aspect of space. I really, really firmly believe that we need to go into commercial space. It does not need to be heavily regulated by as heavily regulated as it is by NASA right now. I understand that the FAA is going to have its 2 cents worth in monitoring things as it does with commercial airlines. But we're not going to go anywhere if we don't go into private space. It's part of the reason that I left NASA ultimately. It's part of the reason that I pursued the Atsa, because that's what I really think is if humankind has a destiny within space, I think it's going to have to go in that particular direction. Now, you can get me waxing enthusiastic further about that. I'm sorry, it sounds a little off the wall, but I really, 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 really believe that. I think that's what it's going to have to go.
thank you.
Sir?
Quick question about patents, and given that the U.S. is one of the only countries to have affirmatively extended patent protection to their nationally registered space objects. Okay, so I was going to ask what your perceived perception is about the importance of using patents to protect technology like Observatory.
It's a good question. I have no answer. I haven't even thought about it. I think we thought it was probably so much in the way of basic materials that we were just sort of sticking together, and it's a pretty easy concept to pursue. That we were thinking that we had patents.
So talk to you after this.
Yeah. Really, I really haven't
I think that's a great place to end. If we have any further questions, we can mingle out the door here. And thank you all very much.
Thank you all for your time. Business questions, I'd be more than happy to give to anybody who would like one. And I would be interested in this.